Okay, welcome back. So we were talking about lists, and the last thing that we talked about was insertion at the very beginning of the list. Okay? Technically we could insert anywhere, and maybe we can talk about that, but we talked about push front. There are a lot of things that you need to keep track of. Let's talk about push back. It's essentially the same thing. And I won't write too much down because it's essentially the opposite of this, just replace front with back most of the time, or first with last. So you have the empty list case and the non-empty list case, and here's how it goes. If we have a list, here it is, here's our list L, it has a first and a last pointer. If it's initially empty, first and last are both null. And in that case, pushing back some value, like 42 or something, is going to make a new node always. And since it's the only thing in the list, it will have a null next pointer. And, well, because it's the end, we're trying to push to the end of an empty list right now, both the front and the back are the same place, so we should be doing this, okay? So the first and the last element is this one node. It's the only thing in the list, okay? So that's that case. And then the non-empty list case is when we already have stuff inside. So L has a first, a last, and maybe, I don't know, they're pointing over here to like 1 and 2 and 3. So this is the state of the list before we call push back. And when we call it with 42 again, we make our 42 node, of course, and we want it to go to the end. And so you always put the last element having null at the end. Okay? So 3, sorry, that should still be blue. 3's next right now is null because it's the old end of the list. What we need to do is link this up. So 3's next pointer needs to not become null. And remember, we can get to 3 very quickly by following the old last pointer. We don't have to go through the entire list. We say 3's next pointer, the last node's next pointer, is this new node that we made because it's the new last. We're pushing to the back. And then also, we must say, in the not-empty case and the non-empty case, the last is changing. Okay? We're pushing to the end. So that is the kind of thing that needs to happen. Okay? So you make the node, set the date of the next value appropriately, set the links appropriately to the existing list, and then set the original stuff. Okay? The first and the last, the actual member variables of the class. Okay? So hopefully that's not too bad. It is a process, but I think I've spelled it out for you, so it shouldn't be too hard. Just for fun, insertion into a random spot in the list. So if you ever wanted to do this, let's say you had a node, you had a pointer, like here's our linked list, 1, 2, 3, and you had a pointer called n that pointed to the 2, and you wanted to add like 2.5 there, like right here. Well, what you could do is the same thing. You make your new node, 2.5, you set its next pointer to be n's next pointer, which is that. You set n's next pointer to now be the new node, and that's how you add one thing, okay? So okay. So if you want to add something after this 2 node, this is what you can do. All right, so now let's analyze insertion in terms of running time complexity and space complexity. running time is the more important one, because we're not using too much extra space. So, if we want to push to the front or the back, let's just pretend it was the front, we make a new node on the heap that is constant time. It's just a line of code, no loops, no nothing. Bring that node into the front of the list. So, what does that mean? We have to set some pointers. We have to set the first pointer, always, potentially the last pointer, and the next pointer of that node also needs to change. But all of these are just a few lines. Constant time, constant time. These are just a few lines of code setting pointers and dereferencing them. Okay? And we set the first. It's all O of 1 stuff. Well, technically, this is just that first thing. This is just kind of a summary, so maybe that's not even code. And then, if it's empty, we have to test. So that's like an if statement, if blah, do stuff. But the test is constant time, it's just an equality check. And then what goes inside of the if statement is also just a few lines that change stuff. Change pointers around. So again, it's constant. It's the sum of all of these constant time things, which is just a slightly larger constant. Okay? Just changing pointers around and making things on the heap. Setting values, testing for equality, and there's no loops. So this is all just constant time stuff. And then space, when we call our push front function, we get, we have a list to work with already, and our local variables inside of the push front function are the parameters, the things that we're going to add. Really, all we need to do in terms of memory is make one new node on the heap, and that is a certain number of bytes. So again, it's constant. And maybe store some pointer variables. So that's just a constant number of extra stuff. Okay, so that's constant space complexity. Isn't that nice? That's beautiful. Okay, let's talk about search. If you want to search through a list and oops. It's technically not part of the thing that you're implementing, but still, this is important to know how to search through things. You'll go through the first and the last. Here's what you can do. If you have a list and you're looking for something, let me just do the simple linked list. 1, 2, 3, and maybe I'm looking for 2. In order to implement this, you have to start at the first node and just keep on advancing your pointer. Okay? That's all you can do. Okay? That is essentially that. So really, you just keep on. You have to do like a loop body for each node in the list. You have to do a comparison for each node in the list, potentially, in the worst case. And that is O of n, time complexity. Because you got to go through the entire list, doing constant time stuff, which is just comparisons, and I don't really need this slide anymore, do I? And that's the idea. And the pointer that you advance is really the only thing that you're keeping track of. You also have some parameters as well, so constant space complexity, because you just have a few extra variables lying around. You can count them. Okay? Has nothing to do with the size of the list. So that is search. You just go through the list and see if the thing that you're looking for, perhaps the 2, is there. If so, you can return like a pointer to it. That's an idea of search. All right, how about deletion? Now deletion, I'll have you implement these 2 in your actual lab, but you should also know how to do general deletion of a specific element. So let's talk about pop front. That removes the front element of the list. So here's my list L, and it's got some stuff. And you should be careful. You should be careful if it's empty, because there's nothing to pop. So that's one thing. And you don't want to get a seg fault. So if it's empty, there's nothing for you to do, but let's pretend it's got some stuff. There. Now, let's, I don't know, just have it hold 1, 2. There. This is our list. And, well, if I want to pop the front, let's pretend that. I need to somehow get rid of this one node right here. This needs to go bye-bye. And what that means is, well, its next node needs to become the new first, okay? And that's the idea there. So how do you do that? Well, you're going to have to set first equal to be like first's next. Something like that. And so first is changing, and you're also calling delete on a certain node. You have to delete the actual node. Okay, so that is popping the front. And it's quite possible, though, that you have a size 1 list as well. There's only one thing in that list. In that case, the first and the last need to become null again. Okay, they both need to become null. That's the one time. So for example, if I had my list over here, L, it held just one thing. Here's my first, here's my last. Held just the node 1. And I went and deleted that thing. Nothing there. Well, first and last, from what we've said, we're changing first already to the correct thing. It's going to become null, but last also now needs to become null. Okay? I hope you see that, because this is an empty list now. And you can check, like, oh, if one of them is null, then I should make the other null, maybe. Something like that. Okay? And so I think pop back is pretty similar. Just replace first with last. All over the place. And also, let's talk about general deletion of a specific element. So again, let's pretend that you have an element that you want to get rid of. And a list. So here's my simple list. 1, 2, 3, and you can imagine that this gets slightly more complicated because you'll have to deal with the general case of like if it was the first, if it was the last thing, things like that. But let's just pretend we had a normal, just a linked list data structure, and we wanted to delete the 2. Okay? So you'll iterate through this list until you find a pointer to the thing, to the node that holds the data that you want to delete. Okay? So you're going to set your n equal to the thing that you want to delete. So deletion involves search a lot, and I want to highlight that. And then it's just a matter of changing pointers around until, and then delete the actual element. One caveat of this, and that's why I'm not really asking you to implement it in your lab, it's kind of tricky, is the following. You need to make n's previous node and have its next pointer point like that. And that is difficult because here's n. I don't have a way to get back. There are doubly linked lists, for example, that have a previous pointer, but we don't have one of those. So you kind of have to store a previous pointer, and you just have to like shuffle them along each time you advance through the list. And there's, of course, special cases when it's the first element. But that's the idea. And I'm excited about this lecture is because I'm now able to, like, you are ready for me to talk to you about ideas. Okay? So you should be able to take this and translate it into code if I ever asked you to. Okay? So that's why I'm not showing you code right now. This is a really good skill to have. Okay? An analysis of deletion. Let's analyze push front or pop front. So what's going to do, if you remember, it's going to do quite a few comparisons. Is the list empty? Is the list have length 1? And you can figure those things out through comparisons. So a few comparisons, but those are all just, you can count the number. That's constant. Let's see here. We're going to swap some pointers around and call delete. And what do you know? These are all constant. And oh man, is that beautiful? Because think of like an array. Think of an array. Like I want to get rid of this 2 right here and make it 1, 3. And then like question mark. I want to like shift everything over. And this might get very complicated when it's a very long array because you got to start shifting a bunch of stuff over. Lists don't have that problem. It's constant. Constant time to delete something. That's beautiful. Beautiful. So this is a constant runtime. And also constant space. Because you're only storing pointers. Inside of that function. All right? So that's deletion. It's not too bad. It really isn't. It's just a matter of getting all your pointers pointing to the right places. And that just comes with practice. That's why you're going to have extra time to work on this. Okay, so then I think maybe push front, push back, pop front, and pop back are like the biggest challenge for you for this lab to start. And then the final challenge for you is to do the big 3. Okay, so you're going to implement the destructor, the copy assignment operator, and the copy constructor. And let's talk about those things. So the destructor for a list, so remember that the destructor just gets rid of stuff. It cleans up when it's time to remove everything. The destructor for a list needs to delete all the elements. Because here's my list L. It's got a first, it's got a last. It's got 1, 2. null, and all this stuff lives on the heap. Okay? When the destructor gets called, it knows that it's about to go away. The list itself is about to go away. But it's our job to clean up all the dynamically allocated stuff. Okay, so we need to get rid of this somehow with the destructor. And so the idea is you just need to iterate through the list. Delete every element. Be careful though, because as soon as you delete this element, you can't follow its next pointer anymore. So you need to save the next pointer. That's all. Copy constructor, honestly not that bad. Because here's like my L1, here's my L2. Let's say L1, first of all. Had my first and my last, set to 1 and 2. And then if I go in and I say linked list, L2, copy that from L1, well, what you should go and do is, don't do the default thing, where, remember that the default thing is just copying all the pointers, so it's going to do that. We want a brand new copy of all these nodes. Okay, so we're going to iterate through the old list, through the list that we're copying, and add the stuff there. Okay, we're going to make a new node. Make a new node. Okay? Iterate through the list and add the stuff. And what do you know? Hint. You can call push back on yourself. Think about that. And copy assignment, the final piece of the puzzle. Don't think I have a lot of room here, so let me make some space on this next slide just to draw stuff. So here's copy assignment. It is, you potentially have two lists. Or you have two lists and they potentially both have information that is interesting and useful. Here's my list 1, here's my list 2. And they've all been constructed. They exist in memory at the moment. So it's got a first, it's got a last. Let's call it F and L, why not? So here are my two lists, and I want to say in code L2 equals L1. So you'll essentially do the same thing as the copy constructor. But remember that you're going to make these two nodes that are brand new. And you're going to make 1 and 2 because you've copied over these nodes to here. And then you're going to set first last to be those things, but you don't want a memory leak, so you need to delete what you already had before. Okay? So this stuff needs to go away. You just delete that stuff. And also watch out for self-assignment, as usual. I have some tests on that as well. So that's essentially all. Destructor, if you think about it, it's iterating through the entire list. Let's just talk about time complexity. And that's going to be linear. Copy constructor is going to iterate through the old list and call pushback each time. So pushback is constant, but iterating through the entire list and calling pushback, you got to do that n times, or n1, where n1 is the size of the list that you're copying in. Okay, and same for copy assignment. Actually, though, copy assignment, it's linear, but it's linear in a different way because you also have to delete your current stuff. So let's say you have n2 things, and the list that you want to copy has n1 things, well, you have to do n2 deletion work, because you have to iterate through n2 things and do constant time deletion. And then you have to copy everything from the original list, which has n1 things. You're going to have to do n1 pushbacks or something like that. So this is going to be big O of n1 plus n2. We don't know for certain which one's bigger, so we say plus, okay? We use plus when we're not sure which is bigger. Is bigger. Greater, let's say that. Okay, that is, in a nutshell, the big three. And I believe in you. You can implement these ideas, and please yell at me in office hours if you're having any trouble at all. Okay? Lots of fun stuff. And all of this, I don't know if we have time to get through everything. We'll try to get through as much as possible, because I do want to get you to GDB. That's important. So you can have many recursive algorithms on lists, and they are easier to implement a lot of the time than iterative algorithms, in fact. So here is how you can break down lists recursively. Let's go back to the original list data structure. Let's just pretend we have a pointer to the first thing. 1, 2, 3. And if you're going to break down a data structure recursively, remember that recursive means you're finding something inside of itself. So where is the smaller list is the question you should be asking. Okay, and so maybe take a second, pause the video, see if you can find the smaller list inside of this big list. And now that you're back, perhaps you said this. And that is unfortunately incorrect, because a list, a linked list, a proper linked list, has its final element have a null next pointer. Okay, so this is not a proper list, but this one sure is. Okay, there it is. You see that? If you just had a pointer to here, it's as if this was a size 2 list. It's no different. You just iterate through that node, go to this node, and then it's null. You're at the end. That's the smaller list. And so you can call recursive calls on your smaller lists to do some solution, to solve some problem. To solve a subproblem. Okay, so that's how you can do it. So the ones that I definitely want to show you are recursive prints. That's very important. So how do we recursively print a list in order? Again, let's have 1, 2, 3, and we'll go through this slowly. So how about this? I want to copy in a few things from last time, honestly. Let's copy in one, two, three, maybe. That would be nice, because then we'd have 1, 2, 3 at our disposal. Whee! So let's print all of that out like this. So let's recursively print our list. And this is in order, from left to right. So I'm going to make a function called print in order. And I'm going to give it my list, and giving it a list is giving it a pointer to its first element. Okay? That's what I should say here as well. Just like arrays are represented by the pointer to their first element, deep down in memory, linked lists are a bit more explicitly even. There we go. Okay, so that is the idea. So if you want to pass a linked list to a function, you pass a pointer to the first thing. So that's what we're going to do. We're going to pass first to our print in order function, which is going to be a void function. And it's going to take a node star, current first element. And this is going to recursively print in order, okay? So let's remember the steps for a recursive solution. We need a base case, and we need a recursive case. So a base case, a very good one is, or you know what, let's do the recursive case first. I'd prefer that, because that will inform our base case decision. Here's a smaller list, and recursion guarantees that it will print that list in order. We get to assume, okay? As long as we build up the solution properly, okay? So if we make a recursive call on this list, and this was n, so print in order, and next will print what? It will solve the same problem for the smaller list, so it will print 2, 3. Okay? Or maybe we can do it new line, 2, new line, 3, new line. So how do we use this recursive answer that we can assume works because of the magic of recursion? Please yell at me in office hours if you'd like to learn more about this magic. We get to assume that we're going to get 2, 3 printed whenever we call this thing recursively. 2, 3, okay? And our job is to figure out where do we print the 1, our first element. That solves the biggest problem. So this recursive call will print 2, 3. Do I call that first and then print the 1? Or do I print the 1 and then make the recursive call? And I think you know where to go. So we need to print our first element before making the recursive call. Okay. And that is the idea with that one. Dun dun dun. So this is what's going to happen. Cout and data, and a new line, and then print in order the smaller list. And I'm going to walk you through exactly why this works. Oops, I'm in the wrong folder. No, I don't have a G++ call. I don't want to retype it. There we go. Hey, okay, so this was essentially the right thing. So the one problem was that we did not have a base case. We got a seg fault. Oh no. That's our recursive case. In the base case, we're going to keep calling on smaller and smaller lists, and eventually we're going to try and print an empty list. You see that? So if we could only print an empty list. In the empty case, there's no list to print. Just print blank stuff. So that's our base case. And above will be the base case. If n is equal to the null pointer, just return, do nothing. Okay, so now this will work and not give me a seg fault. So let's talk about why it works, and then talk about why it works, and then we'll do the opposite. Print in reverse order. So from main, this is what I called. let's just call it print. I called it print on 1, 2, 3. Okay, that was my first recursive. This is my call, my initial call to this function, print in order. Okay, and then we're here, and print in order is going to see its list. It'd be like, hey, is it empty? It'll be no, it's not empty. So it'll print its data. So it'll print its first thing's data. It'll print 1, and then it'll recursively print the smaller list, print the rest of the list, which is a call to print 2, 3. Do you see that? And so print 1, 2, 3 is waiting for this call to return before it itself returns. It's like waiting right here for this call to complete. And so now we're in print in order for the smaller list, for 2, 3. Is it empty? No. So we'll print our first thing's data, and then recursively print the list inside of that. And the list inside of that is just with 3 in it, right? So this will print 2, and then call recursively. Print just 3. Okay? Which again, it's not empty. It'll print its data, and then recursively print a smaller list, which is empty. And this time, because it's empty, it'll hit this case, and it'll just return and do nothing. Okay? So this gets popped off the stack. Then everybody who was waiting for their smaller list to print can now stop as well, because that was the last line of their code. Like print with list 3 was waiting right here, and now that it's done, it can finish its function. It can return. So print 3 is now done. Print 2, 3 is now done. It was just waiting for 3 to print itself. Print 1, 2, 3 is now done. And now we're back in main, and we printed the right thing. Okay, that's the beauty of recursion, and that's why it's working. So recursive print in reverse order is essentially the same thing. So here, let's see if I can copy and paste that easily. Nice. Yeah, I'll even keep that. So print in reverse order, well, let's talk about the base case and the recursive case again. They're essentially the same. So base case, print empty list in reverse order. Well, there's nothing to print. You're good. Do nothing. Recursive case, though, well, when you make the recursive call on, I guess we should call it n, huh? Just to be exact. I'll keep calling it n. The recursive call on n's next, will print the smaller list. We get to assume that it prints the smaller list in reverse order. But what is the order in which we want to do that? We get to assume that when we make that recursive call, it is going to print this list in reverse order. That's what recursion gives us. Okay, we just need to build up the final answer correctly. So when we make the recursive call, this will print 3, 2. And we need to build up the correct solution by printing our 1 in some place. Where should it be? Ooh, it's after this time. You see that? So if we messed up the order for this one, we would have gotten a recursive print in reverse order. Okay? Isn't that cool? That is the only difference, the order of those two lines. And I really encourage you to draw that stack diagram and see why it's going to work, why it does it differently. And again, we give it the initial list, the whole big thing, which is a pointer to its first node. Oh man, it looks like I did something a bit too quick. Let's see here. 2, 3, 1. That is interesting. Oh, I'm so sorry. I copied this, and the recursive call is print reverse. So I printed the smaller list in order. That's funny. So don't blindly copy and paste like I do. Now it works. Okay. That was a fun bug. Alright, so that's that. I have a little bit of time. I think I'm gonna bring reverse first just to make sure that we're doing this in the right order. I would prefer this, I think. Search is pretty easy. Okay, this is the order that I now want. Here's my list. The one that we know and love. Let me erase all these extra things. And let's pretend that we want to search for a certain value. Let's search for 3 and see if it's there. And like return true if it's there, return false if it's not. So we want to recursively search the list for an element, for a data value. And let's see here. The idea is return true or false if we find it. Return true if we find it, return false if we don't find it. The recursive case will search in the smaller list, as we know. So let's say I'm looking for 1. I'll search the smaller list for 1 with a recursive call, and it'll give me back false because it's not there. And my job is, the answer is, well, it's if it's in the smaller list or if it's in my first node. You see that? Check in the first node as well. And that's the full solution. So now we can build a recursive solution to this. So in the base case, is what you're looking for in an empty list? No, it's never there. Otherwise, in the recursive case, search the smaller list, and if it's there, return true. Otherwise, check in your current node, because it might be there instead. Okay, you're looking in 2 places, and you're essentially iterating through recursion. Search for 2, search for 3, search for 1, search for 0. Let's do this. I'll call it search. We get our list. In the base case, we return false, because what we're looking for, let's say int to search for the value, there's nothing in an empty list. We couldn't have possibly found the thing. And that's kind of an ugly way that it did my comments, so let's do that. Works for me. Okay, and also this should be bool because we're returning true or false. Okay, so now in the recursive case, if we're still here, we're in the recursive case, so we need to search the smaller list recursively, and then also check if it's in our current element to build up the correct solution. So it's something like return and data is equal to search for, or search in the return the result of searching in the smaller list using this recursive call. Search for the same thing. Okay, so the idea here is either it's in the smaller list and we make that recursive call, or it's our current first element. As long as we check in both places, we've checked inside the whole list. You see that? This is the recursive call checks in the smaller list, and we just check in our current first element. In that sense, we've iterated through the entire list. Okay? So say search. And we should get, oh, I guess I want to print this out. Oops. Did it work? We should get true, true, false, which is exactly right. Okay? The 0 is not there, but the other two are. They're just in different places. Now, I don't think we're going to have time to get through deletion, so I'm going to have to delete deletion. But it's essentially iterating through the list using recursion and deleting everything. In the recursive case, you delete the rest of the list, then you delete your one node. Okay? That's the way to go always. Recursive reverse is fun because it's going to make a new list, and that's why I want to talk about it. No, no. I just want to draw this little thing. So we want to make a copy of this list reversed. I want to make 3, 2, 1. And I don't think I have enough time to like write it all up, but I'll make it for you to see. It's a bit complicated. So we want to somehow return back a list. I'm going to transform this one into this one. Okay? Let's see here. Yeah, we can update the list, I think. It's probably the easiest way. So let me just give you the high-level idea, and to show you why recursion is very powerful. To recursively, to reverse a normal list, this is like a common interview question, and it's really complicated because you got to save like a previous pointer and then a next pointer, and you got to like keep on swapping them as you go along, things like that. That's no fun. It's kind of simpler with recursion because when you make a recursive call, you know that this is going to reverse that list, okay, and return to you back the first element. Okay, that's essentially it. And then you already have a pointer to this node, and it's now at the end. Just set its next to be your current node. Okay, so recursively, reverse the smaller list, which does most of the heavy lifting for you, and then it's your job to put this one element at the very end. And it's quite easy to do that because you already know where this node that's about to be at the end is. You can set its next pointer quite easily. And then, of course, because this is the new end, it needs to be null. Okay? New ends next to null. So please come to office hours. I would love to explain this to you, but it's kind of beyond, it's pretty complicated. And it's nothing I'm really going to test you on, so I do want to move on to something that will help you in your lab. Okay? Let's talk about this thing called GDB, and it is wonderful. It is hands down going to help you so much for the rest of the time that you're in this class. It would have been nice to have taught this to you while you were working on the vector labs. GDB stands for the GNU Debugger. No, I wanted white. Dude. and that is helpful. Debuggers are nice. So I'm just going to give a bunch of examples here, but the way that you run GDB, to run GDB on a program, I'm going to type a bunch of useful information, and then I'll have to record the last few minutes of this lecture after my office hours. So to run GDB on a program, compile using a -G flag in addition to everything else. So for example, it's going to be like G++ standard equals C++17 blah.cpp -o blah. That's what you had normally. Just stick a -G right there. Okay, that does something very special. It adds debugging symbols, we say. Okay, that's super nice and super helpful. Which like remembers the names of functions and variables and knows which line you're on inside of your program. It's so nice, that -G. Oh man, is that going to come in handy? And then you run GDB. You say GDB on the terminal. You say GDB, and then you pretend to run your program. You say /blah. Okay, and then that'll plop you inside of this thing called GDB. And I'm going to show you an example of all of this, so don't worry. You can say R for run, lowercase r, run, BT, show the stack, and print X, print the current value of X in your program, okay? And there's these things called breakpoints, which I really encourage you to look into, but these are like the things that will be helpful at the moment, because when you get a seg fault, it'll stop the program at that seg fault, and you can say like, what was the value that made this happen? What line am I on? Things like that, which is super helpful, and you don't get that usually. Okay, so here is my simple example, and I'm going to force you to do this in your lab. I don't think I'm making you turn it in though. gdb.cpp. That's fun because it rhymes. So here is a program, and I'm going to make it very buggy. Okay, so I'm going to say int star I equals new int delete I, something like that. And I'm going to come back to you after my office hours and explain how to use GDB on this program. Okay? Just a few more minutes. Okay, I am back. So this is like time travel. For me, it was a few hours. For you, it was a few seconds. So let's get back to where we were. So we made this program, and it has an issue, and we're going to use GDB to fix it. So let's go and boop, boop, compile this in a special way. Remember, G++ standard equals C++17-G. That's the key part. You can get away with not using it, but it includes more things. It includes those debugging symbols that will help you if you do include it. Okay, then we say name of the file, -o GDB as normal, just that -G is the new thing. Okay, now we can go ahead and run the program. That's fine. Honestly, maybe we should call this something other than GDB. Let's call it like GDB example, not to confuse ourselves. Okay, now we'll alright, I'm happier with that. Alright, I'm happy. So we can run GDB example now and have it yell at us. So the way that we run this inside of GDB is we just say GDB, that's the name of the program, and then we pretend to run our program, /GDB example. Okay, so we just plop GDB at the front, hit enter, and now we're inside of GDB. Okay, it's quite large. It says a lot of cool stuff to you. It doesn't really matter. Our program is waiting to be started. So we're going to say R, or you can type out run to run the program and hit enter. This is like a new kind of command line. This is the GDB command line. So you can see then a few things. When you run the program, it tells you when and where this place, when and where this program stopped executing, where the error happened. So it was inside a library function when it happened, and that's probably the implementation of the delete keyword, but we can get back out by showing the stack. All right, so we say bt, or I think it's backtrace, that's the full thing. We can say bt for short, hit enter, and it shows you your stack. So main called delete, which was really calling this free thing, and so on and so forth. But we can see that on line 7, which is that line right there, is where the problem happened, and that can help us. Okay, that's essentially what I want you to use. So, and you can get back up to that outermost stack frame by saying up a million times. Up, 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 up the stack. So now it takes you to where we were in main, and it shows you that line number. Okay, and you can start printing things. You can say print I. It won't really be helpful this time because it is a valid value. It's an address, but it just got freed already, is the idea. Okay, so we can say quit to get out of GDB. You say yes. And that's one example. Let me show some more. Dun, dun, dun. Let me make a function called void and int star I equals null pointer. And this is going to be your life when you do your lab. You're going to dereference null probably a few times, and you're going to want to know why and how it's happening. And this is exactly how you do it, okay? Okay, so this function now is going to dereference null, and we're going to have a problem. Okay? Recompile, rerun inside of GDB with an R, and isn't this nice? It tells us where we were in main. We can see the entire stack, but we're just really inside of main, and then So main called and is on the top of the stack. And sitting in on line 6 is where the problem happened. Okay, we got a seg fault, and so looking at this, you might think that, oh, I think there's something wrong with I. What was I? Print I. It'll show you the value of I at that time. And null is 0. Okay? And you'll usually have extra things that you can output around here. Like if you're talking about a list, you can print the first. You can print the first's nexts. Print the first's next's data. Things like that. That is going to be super helpful for you. Okay? That's essentially all I wanted to show you there. And you can say up and down, move through the stack, if that matters to you, and quit to exit GDB. So these things. Run to start the program inside of the debugger, BT to show the stack and which line of each function you're on, and you can go up and down to move through that stack. Print x to show the value of the variable x that's local to whatever function you're inside of. You can go up or down to get into which function you care about. And then finally, quit to exit. So you're probably going to get a lot of seg faults, and that's the point of the lab on lists. And I would like you to run your programs in GDB whenever you get those seg faults to see which line these things were happening on and what the values of the variables were and what you did wrong. And that will really help, I think. Okay, it's better than just printing a bunch of random things, though that can totally help too. Okay, so that is a quick introduction to GDB. I'm going to force you to use it a little bit. Well, maybe not force in your lab, but you have an optional exercise that essentially did what I just did. All right. Now, that brings us to the end here. Let's go on to some exercises and get you out of here. So, what you can do, and I really encourage it, is notice the good things that arrays can do. Notice the good things that lists can do. We've talked about a few things. All these little operations, like search, O of n. We've talked about insertion, super nice down here. There it is. Constant, time and space, which is so much better than arrays, because we can insert anywhere in our list, constant time, as long as we have a pointer to that place. Okay, we can put stuff in the middle of other stuff. So arrays are good for some things, lists are good for some things. So come up with some ideas where one's better than the other, and vice versa. Alright, then I want you to take a deep dive into iterators. So try to use iterators on a vector now, because they exist. You can use vector iterators just as easily as you can use list iterators. And this is in the C++ standard library. So this is nothing you're implementing yourself. Just use the standard library's iterators. Okay, so go through a vector backwards using iterators, figure out how to do that, and print out the contents. All right, and hints, you could use a reverse iterator, like rend or something like that, or you could use the opposite of plus plus for normal iterators. Okay, so think about those things, and I encourage you to do the same for lists. And probably the most important exercise, and something I can't really force you to do somewhere other than a test, is to go through all these things. This is a great way to study. Go through every operation that we talked about today. Maybe I went through it fast and you didn't, like I didn't give you the full explanation of, say, like the big three's space complexity, things like that. Try and derive them, okay? That is super helpful. And try not to look too much at the notes above that we wrote together. So it's not supposed to be memorization, but you're kind of walking through the implementation in your mind, seeing, okay, which operations are constant time, how often am I doing them, is this in a loop, like is it getting multiplied by some n, things like that. Come up with the tightest bound for a big O notation, for space complexity, for time complexity, things like that. Okay, so that is where I want to leave you. Get started on your lab, but you will have some extra time to do it because of the midterm. Okay, so good luck, and I guess I'll see you in your lab video.